Hello, I'm excited to share with you our work today on adversarial semantic hallucination for domain generalized semantic segmentation. Our problem involves semantic segmentation, which is the classification of every pixel in the input image. The annotation for this kind of problems is extremely costly since every pixel will have to be labeled. Therefore, for domain generalization, the objective is to train a model with a labeled source domain data and evaluate it on the unseen target domain data. However, due to the domain shift between the source images and the target domain images, there will be a performance drop from the source domain data to the target domain data. Therefore, for our approach, we use style images to transform the source domain images to form semantically hallucinated images. These images will be used during training to help improve performance. Previous data augmentation approaches do not account for the class-wise differences between pixels. This can negatively affect performance, especially for the minority class pixels, because in this method, they uniformly stylize all pixels in the image. Inspired by this work on super resolution as shown here, we also use the segmentation output to transform the features. This segmentation output is used to condition the transformation, as I will show in the following slide. Here, we take the segmentation output from the source domain image, and we use it to condition the style features extracted from the style image. We output the scaling values, gamma, and the shift parameters, beta. This sigma value in our work is set as a non-zero value. We also include orthogonal noise to increase the variation in our style features. After having conditioned the style features are then merged with the features from the source domain images to generate the stylized source domain image. What we observe is that majority classes tend to have a larger shift and scale value compared to minority classes, as seen in the figures A and C here. You can see here that majority classes, such as the road, have much larger scaling and shifting values compared to minority classes, which are generally fluctuate around zero. However, after normalizing the shifting and scaling value by the number of pixels, we observe that the majority of pixels share the same scaling and shifting values, with the exception of few classes such as the traffic light and traffic sign. What this figure also tells us is that it is important to use a non-zero sigma value as shown in this slide here, because because sometimes the gamma value might be close to zero, resulting in no style features being present during the stylization of the source domain images. We also compared our model with state-of-the-art approaches, the domain randomization approach by EAL, published in ICCD 2019. Our method demonstrates superior performance on the mapillary dataset and comparable performance on the GTA to cityscapes dataset. Our qualitative results also demonstrate superior performance with ASM, which is a one-shot unsupervised domain adaptation approach. Our ablation study also demonstrates that the stylization and orthogonal noise, together with ASH, improves the performance of the model. Thank you very much for your time.